Okay, sorry, just told me.
All right, so today Jessica's going to be presenting on the effect of the menstrual cycle and sex on the power duration relationship, which is a way of studying endurance across a broad range of power outputs. So remember, hold your questions until the end. If you need something clarified that you're just not getting, feel free to type it in the chat and I'll try to clarify if it's something really important. If it's just a snide remark, hold it till the end, Gary. All right, with that, go ahead, Jessica.
Okay, are we good to go?
Yep.
Awesome. Okay, well, good afternoon, everybody. Thank you all for being here. As you know, my name is Jessica Linde, and today I'll be proposing my master's thesis. So the question I will be presenting today is, does the power duration relationship vary with sex and the menstrual cycle? So during the presentation today, we will be reviewing literature and concepts related to my question to give some background on why I chose this as my research project. And then I will be discussing the methods for my research and finally reviewing my hypotheses. So to start, I will begin by discussing what the power duration relationship is and the different points of the relationship that we will be researching. And then I will discuss what sex differences have been observed in research. And then finally, I will go over what the menstrual cycle is and what effect it may potentially have on exercise. So research has been conducted for decades with little focus on women. A recent study done by Costello and others examined articles published in 3 major sports and exercise medicine journals over a 3-year period. Data was extracted from over 1,300 articles involving a total of over 6 million participants. And despite years of pushing to include women in research, they still make up less than 40% of the research population. Along with this, much of the initial research done in exercise physiology didn't include any women at all. And also the research only done on men hasn't been verified that this applies to women also. So this has continued while a debate on whether or not women should be included in research or if specific menstrual phases must be defined by researchers. It has been said that the menstrual cycle is not able to be controlled for due to fluctuation of hormones and variability of symptoms. With an increase in women participating in sports competitively due to Title IX, it is extremely important to understand how this cycle affects the body. So my study is investigating the effect of sex and the menstrual cycle on the power duration relationship because there is still a lot of work to be done in our field regarding research looking at sex in the menstrual cycle. So what is the power duration relationship? By definition, the power duration relationship is the maximum duration that a broad range of power outputs can be sustained. And it is a common misbelief that the inverse relationship between the intensity of exercise and the amount of time it can be sustained is linear. And we see this illustrated here on this first graph, where we have our exercise intensity on the x-axis and the maximum duration of exercise on the y-axis. But nearly a century of research has shown that this relationship between power and duration is actually hyperbolic at severe intensities, with the asymptote of a curve being critical power. When looking at the graph here on the right, we can see critical power represented by this straight line. So it has also been previously thought that the sustainability of exercise decreased gradually as the intensity increased. But due to the nature of the hyperbolic curve, we see that this nonlinear hyperbolic relationship is reflective of a nonlinear relationship between power output and the physiological factors that lead to fatigue. Along with critical power, there are many other points along this curve. First, we have our maximum max power, which can be defined as the greatest power output that can be generated during a given mode of exercise. Max power is quantified by a Wingate test, during which subjects will pedal on a cycle ergometer as fast as possible for a fixed load for 30 seconds. And max power is reached within just a few seconds of a Wingate test, and it cannot be sustained for more than a second. So for example, here on this graph, we see that the person's max power can be reached within 3 seconds with a power output reached of 685 watts. So next we have our Vo2 Max Power, and this can be defined as, which we see here, the power at which one reaches the maximum volume of oxygen that can be consumed and utilized per unit of time. And Vo2 max power is quantified by performing a graded or ramped exercise test, where an increase in watts continuously occurs until the person reaches Vo2 max power, and then they can no longer sustain pedal RPMs or increase wattage. So for example, here we see that the Vo2 max power can be reached within just a few minutes, and the power output here was reached at about 275 watts. So finally, we have our critical power, which is defined as the highest intensity at which the metabolic strain of exercise can be compensated for, eventually reaching a steady state. So in other words, this is our critical metabolic rate. Critical power is quantified by completing a series of constant load tests at different percentages of the individual's Vo2 max power until they reach task failure. And we can look at this graph and we see this critical power line, which was determined after the subject performed a few different constant load tests, which we can see these tests represented by these other points on the curve here. So whenever you exercise, you are challenging the homeostasis of the body. So for example, when we exercise, we increase our blood flow and recruit more muscle mass. When we exercise, we use our energy stores, such as our glycogen and our phosphocreatine, to produce ATP, which provides energy in the body for our muscles to contract. So as the intensity of exercise increases, the amount of metabolites, such as hydrogen or inorganic phosphates, will accumulate. And when the buildup of these metabolites is too high, we are no longer able to sustain exercise, causing fatigue to be induced. So critical power represents the threshold between exercise that is compensable or sustainable and exercise that is non-compensable or unsustainable. The ability or inability to attain steady state conditions within the exercising muscle and other relevant systems is one of the major factors that determines if exercise power output is sustainable or unsustainable. In compensable exercise, the majority of ATP is resynthesized aerobically, with relatively few fatigue-inducing metabolites being produced. During unsustainable exercise, much of the ATP demand is met through anaerobic ATP synthesis, and that produces a substantial amount of fatigue-inducing metabolites. So if continued, depletion of our phosphocreatine and the accumulation of these fatigue-inducing metabolites typically leads to task failure. So Jones and colleagues had subjects perform 2 time to task failure tests, one at 10% below critical power for 20 minutes and one at 10% above critical power until task failure. So phosphocreatine, inorganic phosphates, and pH levels were observed. And when looking at these graphs, we can see that these black circles represent the exercise that was performed below critical power, and then these open circles represent the exercise that is above critical power. And so when looking here at this first graph, we see that when performing critical power or below critical power, phosphocreatine reaches the steady state level. And when performing above critical power, this phosphocreatine level depletes. When we look here at the second graph, we see that when performing below critical power, again, this inorganic phosphate level reaches a steady state. And when performing above critical power, we see that these inorganic phosphate levels rise quickly. When looking at this last graph, we see that when performing below critical power, we are able to reach pH levels at a steady state. And then when performing above critical power, our pH levels drop quickly. So simply put, when we perform exercise below critical power, we are unable to compensate for these physiological changes in the body. But when we perform above critical power, we exhaust these compensating mechanisms that are no longer able to compensate for this physiological change that occurs during exercise. So mathematically, critical power is the asymptote of the hyperbola. But physiologically, critical power represents the highest intensity of compensable exercise or steady state conditions. Since critical power represents the transition between compensable and non-compensable exercise, critical power is the point where endurance is most sensitive to changes in power output. And since steady state conditions and sustainability go hand in hand, critical power can be thought of as the highest power output that one can sustain, meaning it is also the highest power output that one can sustain without peripheral and central fatigue developing rapidly. So central fatigue is defined as the inability of the central nervous system to recruit relevant motor units. And peripheral fatigue is the inability of the muscle to produce power. So a combination of central and peripheral fatigue is always present, but when exercising at compensable power outputs below the curve here, we see that you can perform for 30 minutes, upwards of multiple hours, with the main cause of fatigue typically coming from glycogen depletion or the inhibition of the central nervous system. But when exercising at non-compensable power outputs, individuals stop exercise in less than 15 minutes due to a combination of central and peripheral fatigue, typically due to a large metabolic stress. So when observing this graph here, I just want to mention that when we are performing at a non-compensable rate, then this will last for a short amount of time, and then we're at compensable, it'll be a longer amount of time. When performing exercise above critical power, we are performing in the severe intensity exercise domain. And exercise falls in this domain when oxygen uptake, blood lactate, muscle phosphocreatine, or inorganic phosphates, and pH levels fail to stabilize. And so in this study done by Burnley and Jones, they had participants cycle until task failure at a constant load. And on the graphs here, we see that the lowest intensity above this critical power is represented by these black dots, and the highest intensity is represented by these white triangles. So on the x-axis here, we have time, and on the y here, we have our phosphocreatine levels, which is an anaerobic energy store. And then here we have our VO2, which is our volume of oxygen. At task failure, during each of these constant load tests, we can see that phosphocreatine always depletes almost completely. And we also see that our VO2 max is matched at every constant load test as well. So overall, what these graphs are showing is that when exercising above critical power, you are fatiguing at the same metabolic state. It doesn't matter if you're performing for 3 minutes or 10 minutes, our volume of oxygen will match our maximum, and our phosphocreatine will deplete, causing individuals to reach fatigue. But what this also shows us is that there is only so much metabolic disturbance that our bodies can manage before we fail. And this manifests itself as a fixed amount of work that we can perform before we fail. And this amount of work is known as W prime. So W prime is the amount of work and its associated metabolic disturbance that can be tolerated above critical power. And once utilized, the muscle will fail and task failure occurs. So W prime is a fixed amount of work that people can generally do above critical power and is very closely correlated to the work between the critical power and the VO2 max threshold of a person. So in a study done by Burnley and Jones, it was shown that the utilization of W prime does not differ between constant load power output tests or self-paced exercise when above critical power. So these graphs have time here on the x-axis, with power on the y-axis, and critical power is represented by this lower solid line. These dashes represent the amount of work that is being done above critical power, and then these dots are the power output chosen. So on the first graph, we see that this person is performing a constant load test, and that the W prime during this test was equivalent to 12.9 kilojoules of work. And then the second graph shows the same person performing self-paced exercise, and the W prime during this test was equivalent to 12.8 kilojoules of work. So despite exercising at variable power outputs, the amount of work that was performed in constant power and self-paced variable power exercise was nearly identical. And this reiterates the idea that when we are working above our critical power, the same level of metabolic disturbance occurs, causing us to fatigue. Mathematically, W prime can be described as the curvature constant, which we see in this graph makes up the bend of this curve. Physiologically, W prime is thought to represent the amount of work and associated metabolic disturbance that can be tolerated during non-compensable exercise above critical power. So we know critical power is sustainable, but based on the power output we can hit at our VO2 max power, we can calculate W prime, which shows us how much work we can do above critical power upwards towards our Vo2 max power. With the research that has been done, what differences between males and females have been observed? Well, Gifford and Collins looked at how the speed-distance relationship is altered with age. The speed-distance relationship is described as critical speed and distance prime, which are just analogs of critical power and W prime. So athletes who competed at the World Masters Athletic Indoor Track and Field World Championships for the past 20 years were used for this study. And so we can see here that we have critical speed on the y-axis and age on the x-axis. And it was found that critical speed was lower in females at every age compared to their male counterparts, which we can see represented here by the black dots representing males and then these gray dots representing females. And this trend follows through with age. So as we can see, women at every age have a lower critical speed, but why is this? What is the cause? Well, the physiological advantages in men include many things, but to name a few, lower body fat percentage, larger heart size, more skeletal muscle mass, higher Vo2 max, and greater anaerobic capacity play a role. So now we will do a crash course on the menstrual cycle. So the uterine cycle contains 3 main phases. So here we have our menstruation phase, and then our proliferative phase, and then our secretory phase. So during the menstrual phase, what's happening is a discharge of blood and the shedding of endometrial lining. And then when we move into the proliferative phase, this is after bleeding has stopped and the uterine lining starts to build back up. And then at this point, we have our ovulation that occurs, which we can see here. And ovulation separates the proliferative and secretory phase. And what's happening is the egg is released from the follicle. And then moving on, during the secretory phase, the lining becomes even thicker as it prepares to possibly receive an egg. So in our ovarian cycle, we are having our 2 main phases identified as the follicular phase, with ovulation separating that, and the luteal phase. And the menstrual phase is on the first day is considered the first day of the cycle. So for my study, we will be focusing on the follicular and luteal phases. So now let's review what the female sex hormones are, or how they are present during the cycle. So we have our estradiol, which is estrogen, and our luteinizing hormone, and these will spike right before ovulation. We also have our progesterone, which spikes right at the middle of the luteal phase. And so for the purpose of this study, we will be using these hormones to verify that testing was done in the correct menstrual phase. So why does all this fluctuation matter anyways? Well, the fluctuation of sex hormones may actually cause improvements in or detriments to exercise performance at various times throughout the menstrual cycle. So these hormones have potential effects on exercise capacity and performance through numerous mechanisms such as body water regulation and metabolism, thermoregulation, sleep, psychological factors, and injuries. So for example, a major effect of estrogen is that it affects the release of nitric oxide, which causes vasodilation. And then also high amounts of progesterone cause the hypothalamus to set higher body temperatures. So now to discuss many of the changes, or now that we've discussed many of the changes that happen throughout the menstrual cycle, let's discuss if exercise tolerance varies with the menstrual cycle. So a study done by Ansel and others studied time to fatigue before and after an intermittent isometric fatiguing task with knee extensors during the 3 phases of the menstrual cycle. And as we see in this picture on the right, subjects were sitting in a chair with their ankle being in place. And then when active, subjects would push out with different forces at their maximum voluntary contraction. And then subjects would alternate between an active and inactive phase where they would rest. So when looking at the results in this graph, we see that fatigability was regulated by menstrual cycle phase, with the greatest time to task failure seen here on day 21 during the mid-luteal phase, and then the shortest time to task failure on day 2 during the menstrual phase. So now we will discuss the methods of my study, including the research design and statistical analysis. The two main questions I will be posing are, do females exhibit a lower critical power in W prime than males when controlling for differences in leg lean muscle mass? And number two, does the power duration relationship vary during the menstrual cycle with critical power and W prime being lower in the early follicular phase compared to the late follicular and mid luteal phases? So for my study, 15 men and 15 women ages 18 to 40 who are endurance trained runners or cyclists will be recruited. And all participants who volunteer will meet the following criteria: no history of cardiovascular disease or heart problems, no history of smoking, endurance trained, which will be defined as those who have run over 10 miles a week or biked 30 miles per week for the past 6 months. And this is in order to minimize the potential for a training effect associated with repeated testing. Also, we will accept females who are not currently pregnant or are not on any type of birth control. Also, we will choose women who have been eumenorrheic for greater than 6 months, which just means regularly menstruating, and have recorded their menstrual cycle for the last 6 months. And then no females with diagnosed menstrual cycle disorders such as endometriosis, dysmenorrhea, or polycystic ovary syndrome will be accepted in the study. So the first visit of the study will begin with reviewing the requirements of the study with the subject providing written and informed consent. The subjects will also complete a health history questionnaire and a pre-exercise screening questionnaire. All subjects will complete a 7-day recall of exercise and report endurance training over the last 6 months. Females will take a pregnancy test to confirm they are not pregnant, and they will also complete a menstrual symptom questionnaire, as well as report the start date of her last 6 menstrual cycles. So if the subject qualifies to participate in the study, then we'll move from consent and do a body composition scan, which will be measured by a DEXA. And then the subject will perform a Vo2 Max test, followed by a 30-minute break, and then a verification test. On the second visit, a max power test, which will be determined by performing 3 5-second Wingate tests. And these then 2 assessments of critical power will be performed for familiarization of the subjects with time to task failure testing. And female subjects will complete these first 2 testing visits on any day of the menstrual cycle. But at this point here, females will be assigned to start testing during one of the 3 phases of their menstrual cycle. So these phases include the early follicular phase, which occurs around day 2 to 4 of the menstrual cycle, and then the late follicular phase, which occurs day 12 through 14 of the menstrual cycle, and mid luteal phase, which is approximately day 22 through 24 of the menstrual cycle. These tests will be 24 to 48 hours of each other, all the 2 testing visit days. And then a group of males will also complete their testing visits approximately 10 days apart to mimic the menstrual cycle phases. So on the first day of the selected phase, blood draws will be taken to analyze hematocrit and hemoglobin, and then that will be in all subjects, while estrogen and progesterone will be measured in female subjects to analyze and confirm that these females are in the correct menstrual phase that we think that they are. Subjects will then complete 2 critical power tests with a 30-minute rest separating the 2 tests. And the constant load for the first test will be approximately 85% of their GXT power. And the constant load for the second test will be at approximately 100% of their GXT power. And the load may be slightly adjusted dependent on time to task failure on visit 2 testing. So on the second day of the selected phase, subjects will perform a maximum power test to determine their maximum power output, and then subjects will complete 2 critical power tests with 30 minutes rest between each test that day. The constant load test for the first test will be, or the power output for that first test will be approximately 80% of their GXT power, and the constant load for the second test will be approximately 90% of their GXT power. So the load may be slightly adjusted dependent on time to task failure on the previous day of testing. And then subjects will come back for 2 more phases following the same protocol. A combination of factors will be looked at when determining testing days, including blood draws, menstrual mapping, ovulation testing, and symptom tracking. Blood draws will be performed on the first day of each testing phase to evaluate progesterone and estrogen levels using an ELISA kit to confirm females are in the correct phase. Menstrual mapping will be used, which is the recorded start and end date of the female's last 6 menstrual cycles. And then ovulation tests will be performed daily, starting on day 7 of their menstrual cycle. And these tests will be continued until ovulation is achieved and will be used to confirm the start of the luteal phase for each individual. On the screen, we can see a picture here of what the ovulation test strip looks like. So during the study, women will be given a printed calendar, and with that, they will record their daily symptoms. And then throughout the month, women will also be recording their ovulation test numbers, as well as their bleeding range, for example, their spotting or heavy bleeding. So to describe the power duration relationship with critical power and W prime, a series of 4 constant load tests done at different percentages of the individual's maximum power output reached during their graded exercise test is performed to task failure. Each of these tests must be completed within 2 to 15 minutes and reach about 95% Vo2 max to be considered an accurate test for determining critical power. So typically, all tests are completed at powers greater than 65% of their maximum GXT power. So a critical power test will begin with a calibration to the metabolic cart, followed by a 5-minute warm-up at 40% of their GXT power. And then at minute 4, their rate of perceived exertion will be assessed by the Borg scale. And then a 5-minute rest period will come next, followed by a 3-minute rest period or 3-minute warm-up period at 40% of their GXT power. And then after this, the wattage will be increased to a given power output. And subjects will be instructed to maintain a pedaling frequency of 85 to 90 RPMs, and their time will be recorded during the duration of the time to task failure test. And the task failure will be determined when the subject is no longer able to maintain a pedaling frequency of 5 RPMs less than their self-selected pace for more than 5 seconds, despite strong verbal encouragement. The subject will then cool down at 40% of their maximum GXT for 3 minutes. So once all tests are completed, the time to task failure at each power output in seconds is graphed against the amount of work in joules, which is converted from the power output. So this should produce a linear relationship between time to task failure and work performed. So for example, if a subject completes 4 constant load tests at 65%, 70%, 80%, and 100% of their maximum power output achieved, this is what we would see. So at 100%, they work at 200 watts for 156 seconds. At 80%, they work at 160 watts for 291 seconds. At 70%, they work at 140 watts for 492 seconds. And at 65%, they work at 130 watts for 760 seconds. And the slope of this line represents the individual's critical power. The y-intercept of this line represents the W prime. And to ensure that an accurate critical power and W prime calculation is performed, the standard error for the critical power should be less than 5%, and then for W prime, less than 10%. A mixed model ANOVA of 2 groups with 3 repeated measures will be performed to determine the impact of biological sex and the menstrual cycle phase on critical power, W prime, and max power. In the event of a significant F value, post hoc testing will be performed with Bonferroni corrected t-tests of planned comparisons, and the reproducibility of measurements will be determined with intraclass correlation and coefficient of variation. If a significant effect of menstrual cycle phase is detected from the mixed model ANOVA, a reproducibility measures will be considered separately for male and female subjects. The alpha for the statistical procedure will be set to 0.05. Finally, we will discuss my hypotheses for this study. So in the study, simply put, we have 2 main questions. Number 1, What sex differences are observed when comparing critical power and W prime? And number 2, does menstrual cycle phase influence the power duration relationship? So regarding sex differences, we hypothesize that females will exhibit the same critical power as men, but a significantly lower W prime than males when controlling for differences in lean leg muscle mass. And then regarding our menstrual cycle phase, we hypothesize that the power duration relationship will vary during the menstrual cycle, with critical power and W prime being lower during the early follicular phase than during the late follicular and mid luteal phases. And this concludes my presentations. What questions can I answer?
All right. So thank you, Jessica. Good job. I'm sure if we were in person, everyone would be clapping right now. So we'll open up discussion for questions. You can type it in the chat, or you could just start talking. This isn't limited to just her committee, so feel free, anyone can ask a question. And it looks like Mo, a PhD student here at BYU, has a question for you. So take it away, Mo.
Sorry, do you hear me?
Yes.
I just wondered what was your reasoning for choosing this method of warming up, because I know that you've been used this method in lab for a while, but I don't know what your reason is that for like warming up for 5 minutes at a lower percentage and then resting and then warming up before starting the exercise. Because based on what I've studied, it seems that warming up like at higher than critical power and then resting between 10 to 30 minutes afterwards has resulted in a better performance. So I was wondering what was your reason to pick that type of warming up?
Yeah, so your question is, why do we do a 5-minute warm up, then 3-minute rest, 5-minute warm up?
Right.
So to my understanding, what I think the reason we're doing that is because with the like metabolic state, I think that we just get better results when using the metabolic cart, when we have those different things. So for example, like I mentioned, we have a quick calibration point. And as we know with our Vo2 Max, when it comes to peak or starts rising, that's obviously not going to happen. And we're going to reach steady state within just a few minutes. And so to my understanding, that's why I think that we're using that. It just helps with the calculation of the like Vo2 Max and the Vo2 that we're looking at. But Dr. Gifford, do you have anything else to add on that?
Most of it just has basis, and that was what was recommended in the literature from people who've been doing it for a while. There might be ways to get slightly better numbers here or there, but what's most important is that you're consistent. And so we're consistent across trials to make sure that we get.
Okay, that makes sense. Thank you.
But it is a good question.
Yeah.
Hi, Jessica. This is Rob. Can you hear me?
Yes.
Hey, so I have a quick question. Sorry, I was a little bit late to the presentation. But my question has to do with inclusion and exclusion criteria for subjects and fitness level. So it seems that having subjects with the same sort of fitness level is important in both the men and the women. And you're going to do a Vo2 max test. So will you exclude subjects based on that test? So is that an inclusion exclusion criteria? They have to have a certain fitness level on that test. And are you going to match the men and women for fitness? So for example, match them by their Vo2 numbers.
Yeah, so we will be matching them by fitness and Vo2, as well as matching them towards their like lean leg muscle mass. And that's like our main thing. And then regards to your other question.
So when you say control, when you said you're going to control for lean leg muscle mass, this isn't a statistical control. You're actually going to match them for lean mass. Do you think you'll have trouble matching them for lean muscle mass, given that men typically have a much higher
Yeah, so far with our results, like our pilot data, it hasn't been too much of a problem. We have been able to match them before. So yeah, it's not a statistical match, but it is controlled for with our variation. But so far it seems to have been working well.
Okay.
I would say it's most likely going to end up being a statistical control.
Okay.
Yeah. It's hard to get the men and women to have the exact same muscle mass.
Yeah.
Right. Okay, thanks, Jessica. By the way, good job. It's a really cool project. Interesting.
Thank you.
Okay, other questions? If you don't start asking, I'm going to start volunteering you to ask questions. So I'll ask, so Jessica, the hypotheses that you have, well, first, before I get to that question, you presented one study, I think it was in Ansdell or something like that, where they showed time to task failure is down during menstruation. Is that the only study, or surely there are more?
Yeah, that's a great question. So I have a slide for this. Where is it? Okay, so there's actually a meta-analysis that was done by McNulty this last year, and it looked at, I think, over 70 different articles. And so this one specifically was looking at Vo2 Max and the effective exercise performance. So there has been a lot, I don't say a lot, there has been a good amount of research done on this, but where I think we are, specifically on the menstrual cycle part of it, where we are special with this research, is that recently it's been come to our attention that when doing a menstrual cycle study, we need to do an appropriate confirmation of menstrual cycle phase. So, for example, historically, menstrual cycle studies have been done primarily using menstrual mapping as the main way to predict the menstrual cycle phase. And we can see here that there's large variability when predicting like the phases with this method. And so like we have 63% when using this method, or 67% yes and 33% no. And obviously we don't want there to be that much of variation. And so I think we just need to do better at including our blood draws, and also looking at our luteinizing hormone, as well as doing this menstrual mapping to be able to get them as close to the right phase as possible.
Okay, and there's a lot of variability on when they test, isn't there?
What do you mean?
We were talking earlier,
Oh.
isn't it that like very few actually do the testing during menstruation?
Yeah, so what's unique about also like that Ansel article is they do the early follicular, the late follicular, and mid-luteal, and a lot of research actually just does mid-luteal and mid-follicular. And so that was like another really popular study that's come out recently. Did I pass it? Yeah, like this one, which is a really good put together study. It only looked at the mid-follicular and mid-luteal, but what's interesting about that is that's not when we see those hormones actually peaking. And so I chose to do my study at these points because that's when we see the most variability. At least that's what I hypothesize.
Okay. And so what were the conclusions of that meta-analysis?
Yeah, so the meta-analysis, it said that the results were like trivial, that there wasn't much of a difference with the early follicular phase compared to all of the other phases, but they made a large focus of their conclusion being about the reasons why. And so they identified large between study variance, and then that there's a range of other factors such as small participant number and high sampling variance. And then also there was, training history was different, and that could also have led to this large between study variance that was observed. And so even though, it's looked at everything, it was telling us that going forward, we really need to make sure we are in the appropriate confirmation of menstrual phase testing.
Okay, all right, thank you. I think Abby has a question for you.
Yeah, so my question, you kind of answered it. I was going to ask about why you picked those phases, but and like why you picked to measure those. But I was wondering if you could actually go into a little more detail of like how, so right, you're going to measure it within the first 7 days, is that correct?
Mhm.
So are you going to try to make that consistent across like, right, because if someone's cycle is a different number of days,
Mhm.
so would you,
Yeah,
I guess,
great.
how are you going to control for that variation between people and like those?
Yeah, for sure. Great question.
That makes sense.
So the dates we've set, yes, like in a perfect world, what we see is that an average menstrual cycle is 28 days in length. But so if, for example, the woman we would have them come in right like day 2 through 4, and then 12 through 14, and then 20 through to 24. But the reason that we're doing our ovulation test is that actually helps us determine when to do our mid-luteal phase. So, for example, when we have, we'll have our menstrual mapping, which is the last 6 months of them having been recorded. We're only accepting them if they've been recording them for 6 months. And so hopefully we have a really good idea, like this girl is 30 days, but like you're saying, we're not just going to assume that day 15 right in the middle is when ovulation occurs. And so obviously we know day 1 will be menstruation, and the researchers will be notified at that point and have them come in the next day. But then here we will see our luteinizing hormone when it starts to rise and peak. We will have them, we will use that to know ovulation occurs within the next like 12 to 24 hours. And then we will go off of that. So say that their ovulation occurs on day 15 or 16, we will go 7 days after that to predict their mid-luteal phase. So it will be dependent on a variation of things.
Cool. So you'll have them come in for that follicular phase when they start increasing that the luteinizing hormone,
Yeah.
and then just 7 days after that.
Yeah. So, so essentially it is after menstruation. The good thing about estrogen is it's a larger, progesterone, I guess too, luteinizing hormone peaks a little steeper. So we will get them in, like I said, day 12, about 2 days before we think they're going to ovulate, dependent on the menstrual mapping. So that's about 10 days after. But then using luteinizing hormone, that'll help us predict more of the mid-luteal phase is what we're going to use it for.
Gotcha. Okay, cool. Thanks.
But the goal with that menstrual phase is to get them in as close to day 1 or 2 as possible, right?
Yeah, preferably day 2 and 3, just because on the first day, women aren't bleeding as much. And so we want to get them like the true effect of the actual menstruation. So hopefully day 2 or 3.
Great. Okay, Dr. Mack has a question for you.
Okay. Am I on?
You are on.
I can't tell. Anyway. So the assumption is the influence, I think the assumption is that the influence of the hormones is what's causing the problem. What's the evidence for that?
So specifically for like our study, we're not going to base like the difference found during the phase on the specific hormone. We don't want to say that that's like a cause and effect. Right now, we're just using the actual hormones to confirm that they are in those phases. So that's the main purpose of it.
So if it's not the hormones, what's causing the changes in physiological function that produce this change in performance?
Yeah, so with the Anzel study, which was I think it's actually the next slide. This one specifically, they did find differences in like neuroexcitability and different effects of progesterone and estrogen. So like after doing my research, I would assume, yes, it is related to hormones, but because there's not a ton of research out there that has followed the 3-step method that I mentioned, I don't want to just go ahead and say like, yes, it is these hormones. First, the first purpose of our study is just to see if if there is a change, and then if there is one, or the next question would be what specifically is happening there.
Jessica, you've talked about this in the past, just name some of the impacts of what these hormones do to relevant physiology.
Yeah, so I mean, I mentioned very simple ones like so estrogen will release nitric oxide and cause an increase in vasodilation, and obviously our estrogen is highest right before ovulation, and so there have been some studies that have shown greater strength during that phase when estrogen's highest, because we assume we can get more blood flow directed to the right areas. And then progesterone, like I mentioned, it has a thermoregulating effect, and so it causes the hypothalamus to increase our body temperature. And so there's just a lot of different things like that are occurring. But yeah, so there are major effects. It just will be interesting to look at. For example, this one was specifically looking at a few muscles within the quad or in the knee extensors, I guess. And it'll be interesting to do more of a full body exercise and see if we see similar things along with the hormone pattern.
Hey, Jessica, I have another question. I guess it kind of follows up on that one. So it seems to me that, at least in this study that you have up on the screen here and in your hypothesis, that always the time to task failure is lower in that, was that the early follicular phase? So that's when they're menstruating.
Yes.
So what's your explanation for someone that would just say, well, they just can't go as long because they're uncomfortable, because that isn't menstruation typically associated with pain, cramping, and so forth?
Yeah.
Is
So
it just that, and what can you speak to that, I guess?
I would say that is a big influencer, but also besides that, like if the example I gave with estrogen right now, if there really is a difference in our, how much estrogen we have and how much blood flow there is, obviously that's going to, directly influence like our exercise performance. But with our study, let me go to the end here real quick. Okay, so for our study, we are going to be first using a menstrual symptom questionnaire. And so based off of this, we're hoping to be able to see, kind of how they perceive their menstrual cycle and like actual menstruation. So for example, it says like I have abdominal pain or discomfort, which begins one day before my period. And so we'll be using this to see how they, how they actually feel, like what physiological things are going on, and then how they interpret it. And then hopefully after tracking like all of their symptoms for a month with our calendar, we will be able to see how they feel throughout the month. And then if there is this difference, it'll be interesting to see, for example, if in our study we find in the early follicular phase that performance is lower, it'll be interesting if, for example, all the women that day who are lower are, they say that they feel horrible versus people who feel great. Like it'd just be interesting to look at it that way. At least I'm curious to see, because then I feel like we'll get a good idea of if how they perceive it, how much pain they're in is actually influencing it, or if there is no difference. That would also be interesting too.
Okay. And then one other question, is it, maybe I missed this in the study design, but you're not doing blood draws and verifying like hormonal levels or anything? Or
Yeah, yeah.
You are, okay. I totally missed that. Okay,
No, you're
never mind then.
Yeah. Rob's question about just feeling crappy during the period, I think it's super valid, and it should. My guess is it would probably show up in an impaired performance. If the performance is impaired because of that, it's a real thing, and most likely we would see it, if I had to guess, in a decreased W prime, or how much work you can actually tolerate before you fatigue above critical power. So that's my guess, but
Can we experimentally induce cramps in the men, and just as a control?
Studies where they people have induced pain like in one leg, and then had them do the exercise in the other, and like that W prime is down. So like definitely discomfort or pain can influence your performance, probably by like a central inhibition of the motor unit recruitment. Okay, other questions? Insights?
I have a question.
Oh, great. Nani.
Can you hear me okay?
Yeah.
Yep.
Okay. Maybe I missed this, but are you gonna quantify testosterone at all, even in the females? Because theoretically, couldn't the females with more testosterone potentially perform better? Would you control for that or anything?
Yeah, so kind of like I mentioned, we're not specifically looking at estrogen and testosterone or progesterone to say like these are what are causing the changes. So we aren't looking at that. We're only looking at estrogen and progesterone for the purpose to confirm that we are in the right phase. So that's why we're not going to be controlling for testosterone.
Gotcha.
But I mean, it is a good point. Like there obviously could be differences there.
Great. If you find yourself thinking about this over the next couple of days, especially if you're a woman and you have insight or suggestions for Jessica, I'm sure she would appreciate them. She's working with me, a man who's never experienced a menstrual cycle, at least firsthand. So she could use someone to talk to about it. If there are any more, I'll leave it open for more questions from everyone. If not, we'll break down just to Jessica and the committee. Last call. All right, so you guys can give Jessica a round of applause for now. What we're gonna do is we'll dismiss everyone except the members of our committee, and we'll meet with her and she can inform you on the outcome later.
Good job, Jess.
Thank you.
Good job, Jess.
Good job.
This is also where we find out who actually made it all the way through your presentation. I just learned how to remove people. Uh-oh, I lost it. Okay, it looks like it's just us now. Okay.
Jason, I asked most of my questions in the regular session there, so I don't have
Okay.
any more extra questions. Maybe just if we want to talk through any, that might be helpful talking through any issues. Maybe you might come up with recruiting or anything, any way I can help do stuff, other stuff.
Yeah, that'd be great. What do you got any questions for Rob, Jessica?
No, except one thing that comes to mind is Brandon's study is super cool. We talk like once a week, so
Yeah, so these studies are going to overlap a little bit. So I'm kind of knee deep in thinking about some of the challenges associated with recruitment and retaining these women and being able to accurately sort of assess menstrual cycle and so forth. So I've never done this either. So yeah, I don't know. Do you anticipate? Do you think? Have you ever recruited women for a study like this?
Me personally?
Or Jason or any? Yeah.
I haven't done one across the whole menstrual cycle, but the majority of the studies I've done in the past, we always have to get women in during menstruation, the first 7 days of the period.
Yeah.
And that's not too difficult to do. So we'll see how it'll be to get them in more times. But yeah, it's going to be an adventure.
Okay. The only, when in reading through the proposal and listening today, the only thing that I could think, the only real big challenge I thought is just, it seems to me that matching them for physical activity is just exceedingly important. Am I wrong about that? Or and getting the right subjects with, you know, that are all relatively, you know, very active, and matching that portion of it, if you're going to be able to detect these differences, the subtle differences that might occur within the different phases of the menstrual cycle. So
Yeah, so how are you going to do that, Jessica? How are you going to verify physical activity and all that?
Yeah, so for recruiting, obviously, I don't know how this will end up at the end of the day, but where my mind goes to is I like personally want to, I mean, my age group is 18 to 40. In my head, I see it panning out to be a little bit of an older group. I specifically am going to reach out to like cycling clubs and things like that, just because I think I don't know, I think if I present my study in a way where it's like, hey, come make a difference in exercise physiology, like this is a different, you know, we don't do lots of these studies, and hopefully that'll motivate them and get them in. And so, you know, I have a brother who's a marathoner and sister-in-law who's a pro cyclist. And so I'm gonna start with those avenues, obviously regular recruiting. And so obviously if they're training together, then they would be able to be matched, which I think would be really nice.
what about cyclists versus runners? Do you think, is there any reason to believe that they would, because of the mode of exercise is quite different, any reason to believe that they would respond differently to the exercise that you're having them do to measure critical power?
Yeah, so I mean, like we know if you are a runner, for example, and we put you on a bike, you're going to have a little bit lower of a VO2 max. And so I do think that there could be a difference. So I would definitely want to match them based off of like if they're runners or not, because the mode is just super important. So for sure, I do think that it could influence it.
And you got the 2 familiarization days ahead of time that
Mhm.
should help a little bit with that. But yeah, that's definitely going to, if you had all guy runners and all girl cyclists, that would be a problem.
Mhm.
Yeah.
And then with like the lean muscle mass, dividing, so a lot of the difference in performance in men and women is just due to how much weight they're carrying around relative to their muscle, right? Their body composition, with like the women carrying around more body fat. But when you look at it with the DEXA, with the lean muscle mass, at least in the initial pilot data that we have from other studies, when we compare VO2 max between men and women, even though like if you're dividing by body weight, it's super different, but by lean leg mass, it's almost identical. So we'll be able to at least covary for lean muscle mass and see, I think. Gary, do you got any more questions or suggestions, thoughts?
Is there literature on endurance performance influenced by menstrual cycle? Not critical power, but just endurance performance?
Not a ton, if I'm being honest. I don't think so. I'm trying to think what I had on my, the only one that comes to mind. I think Dr. Veers did it. No.
No.
I sent you a long time ago.
How about this one? The effects of menstrual cycle phase on physical performance in female soccer players. 2000 and
Yeah, I think I saw that one actually.
yeah. So what did they find? They found that during the mid-luteal phase that their performance was reduced.
Yeah.
And
right.
so you're just going to critical power, which actually should be reflecting of somebody's ability to perform endurance. So I would just look at those studies, looking at just endurance performance in the literature to maybe make sense. I mean, the study you cited by Ansdell, that's just power output of the muscle, and he showed only a decrease in power output, or what you call force production, during the mid-luteal phase too. So, and not during the mid-follicular phase. So I think it's only occurring, the literature pretty much supports the change during the luteal phase, but not during the follicular phase. Does that make sense?
So opposite of your hypothesis, basically.
Yeah. At least in certain performance things.
Yeah, I mean, yeah, I totally know what you're talking about. Now I was trying to think of what it was, but yeah, this one article that I read talked about like brain economy, how it was lower in the mid luteal. What I think, like specifically why I think what I think is, I mean, I don't know about that specific study you're mentioning, but like even today when Dr. Gifford and I were talking, most research that we're looking at, it's not looking at the early follicular when I think that the lowest point will be seen. They're mostly looking at mid follicular. And so that's, I don't know if that makes sense, but essentially, I don't think that they're looking at the exact same part of the phase. And so
they may be off a bit, but there isn't much support for anything going wrong in the follicular phase. It's always in the luteal phase when progesterone's released.
mm.
Yeah,
What the heck is progesterone doing, man?
But we're also in this study, you're looking at something different. You're not looking at endurance performance per se.
Oh, that's critical power is endurance performance.
yeah, it's like it's endurance.
Mm-hmm.
Right, but it's like, how are these other, I mean, you can measure endurance performance in a million different ways. Like these people could be,
Absolutely.
so I think that matters when you look at these studies to see how they're measuring it, because maybe they're measuring it at underneath critical power the entire time, right? And so it may not mean much in terms of relationship to her hypothesis on critical power.
I don't know the answer to that. I don't. I mean, if you're measuring someone's VO2 max at different phases of the menstrual cycle and find that it's lower during the mid-luteal phase, but not changed during the mid-follicular phase, that's VO2 max is lower than the lower energy. What is it? Lower than the critical power, but
Yeah, it's going to be interesting. I think that's important that she's doing these 3 different phases just to see. But there, to Gary's point, there's some like an easy area for research, just looking at like women's performance, like professional athletes, those that have a cycle, seeing where
that's another way.
yeah. So if they're performing best during one phase or the other, just based on their race times. And there's some studies on that. I don't remember how it pans out. I don't think there was anything super big about it, but it'll be interesting. My hope, if I'm fully honest on this, my hope is that we find that there's little to no effect of the menstrual cycle, so that future studies, we don't have to worry about it at all. But we'll see.
You could just do what everyone does in the past, just only do it on men so you don't have to deal with it.
Yeah.
Which is why there's probably not a ton of studies out there on this very thing.
Okay. So do you guys want to dismiss Jessica so we can discuss, or are you okay just talking right here about what you want her to do?
I'm good dismissing her.
You want to dismiss her?
Dismiss her.
Okay.
I don't have any further questions for her.
I think you've done a pretty good job trying to address all the problems you can run into with this kind of study. So
yeah.
Thank you.
Okay. So do you want to vote if you're in favor of passing her or now in private, or do you want to do it in private or just do it now?
I don't need to be private about anything.
Okay, that's fine.
I vote yay.
What?
Okay, so are you both okay having her proceed?
Yes.
Yes, I'll sign the receipt, whatever. We're supposed to sign something, so just have her drop it by and we'll sign. Oh,
Yeah,
I'll sign it.
grad progress. I'll type in the link in the chat. So you just have to go to this link and sign in.
Oh no, I gotta get online somewhere.
Yeah,
Oh gosh,
you can
okay.
approve it. So there's no paper anymore.
Oh, that's it. Yeah, I forgot.
But I do appreciate all your insight on this, Gary. You've been really helpful figuring out how to do this. Considering all the moving parts, it's not going to be easy.
No.
We do have, I don't know if you saw, but we have Alan's offered to sponsor a phlebotomy course. So
I heard that.
the
I'm not
IRBs
sure why.
Yeah, I had the same response, Gary. Is the IRB giving you trouble
They
about
are, yeah. They wouldn't let me do a blood draw without it. And so I just said I was going to go do it. And Jessica, we were going to go do it. And then apparently Brad has had the same problems. So now Alan's just saying, let's get whoever wants it can do it. So that'll be at the end of July.
I'll probably sign up for it, but I have never had any trouble drawing blood.
Yeah, it's funny because they've passed it before with me not being a phlebotomist, but this time they said you need to be it. So
Who's on the? But can you look up the committee members so I can yell at them?
I can't.